All right, hello 20-1 students. So today we are starting with chapter 4, looking at quadratic equations. And you'll notice at the beginning of your blank set of notes, there's kind of an outline of the different sections that you'll be covering and how many days you should be spending on them, including the review at the end as well as your unit exam there. Okay, so you should be using that as a guideline for, how you should be completing your studies. So we're going to start out with lesson 4.1 here, which is looking at how we solve quadratic functions graphically. So basically, how do we draw a graph that's going to help us to solve for a quadratic function. So we start out here with a little bit of an investigation. Each water fountain jet creates a parabolic stream of water. Okay, so if you think about if you've ever seen like a water fountain where the water kind of shoots out at an arch, that's what we're looking at here. You can represent this curve by the quadratic function, which is h of x is equal to -6 times by x minus 1 squared plus 6. Okay, and so h is representing the height of the jet of water, and you can see that down here on the graph. H is on the y-axis here, so the height of the water, and x is the horizontal distance that the jet of water is going to travel from the nozzle. Okay, so basically this drawing is representing what's happening. So you can tell according to this that the way that they place it is that wherever the water comes out of the nozzle is basically at 0 for height, and they consider that like kind of the origin, or 0 on the x-axis for horizontal distance. And then the water's going to shoot up out of there, and it's going to reach a maximum height and curve back down. And you can tell that what is supposed to be happening here, they say that the light is placed right here. So basically wherever the water hits, like the jet of water hits the surface of the pool, is where you would want to have your light placed. Okay. So the other thing you can tell in mathematical terms, so this is like kind of visualizing what it looks like in real life, but in mathematical terms, if you think about where the nozzle is and where the light is, what can you say about what those 2 points represent on the graph? Well, you should be able to say that those represent the x-intercepts, right? So it's where the graph crosses the x-axis. So using your graphing calculator, you're supposed to graph the quadratic function. Okay, so just keeping in mind some of the basics for this, we want to go into our y equals in order to do graphing. I'll try and move this up a little bit here. And then we want to put in, let's see, there we go. I think you guys will be able to see everything there. Okay, so we want to put in -6. Now keep in mind it's really important to use your negative button for this. So that's this one, not the minus one. So -6, and then bracket x minus 1. So remember your x variable is right there. X minus 1, close the bracket, square it, and then plus 6. So make sure whenever you're entering in your functions that you are following whatever is written exactly in your calculator. Okay, so now we have our function and we want to go to a graph. So if we go graph, so I have my graph set to standard settings, which seems like it's good enough for this graph, so we can see the whole parabola there. And so basically they're asking us to graph it, and you can see that the sketch of this graph has been added in here. So based on what we see here, we want to ask how far from the nozzle should the underwater lights be placed. Now in this case you're kind of given this, so it's pretty nice because you can count it on there, but keep in mind if you need to use your calculator to determine this, we're trying to figure out how far from the nozzle should the lights be placed. So basically we're looking for this point on the graph, right? Because we want to solve for the distance from 0, which is the nozzle, out to the light. So if you're looking for x-intercepts, you press second function trace, and then you want to choose 0. And then remember, you always have to select your left bound and right bound. Now, if you weren't sure, you might want to double check and make sure this is crossing through 0. So we can do that real quick. Left bound, so you want to be to the left of where you think the intercept is. And then right bound to the right of the intercept. And then hit enter one more time because it's going to guess for you. So here it says, yeah, sometimes, I'm not sure why the calculators do this sometimes, but if you get like a crazy exponent, like something to the power of -14, you can assume that that pretty much means 0. And then y is 0. So basically x is 0 when y is 0. So we know that this nozzle is at 0, 0. So we can just write that in to keep note of it. Then we want to check out where the second intercept is. So again, second function trace, choose the 0 option, and then you just want to be on the left side of this intercept. So we can hit enter there. Then on the right side, hit enter again, and then guess, enter one more time. And you can see that when y is equal to 0, x is equal to 2. So basically our other location here is 2, 0. And you could probably tell this by looking at this drawn in one, but I wanted to make sure that you're familiar with the technique you would use on your graphing calculator for that. So how far from the nozzle should the underwater lights be placed? This is, like for this one, it's pretty easy because our origin was at 0. Sometimes you'll be asked for a horizontal distance and your origin won't be at 0. So remember that you always have to just find the difference between the two x-intercepts. So like if the origin had been at 3 and the other x-intercept was at 5, the distance would still be 2, right? So just making sure you find the difference. So how far from the nozzle should the underwater lights be placed? They should be placed, let's see, the measurements are in meters, 2 meters from the nozzle. And again, like I've kind of mentioned to you guys in other lessons, on the filled in notes, I have the better answer that would be more like what I would expect to see on a written question in a test. So make sure you've read that so you get a better idea of how to properly answer on tests. Next one, why do you think the x-intercepts of the graph are called the zeros of the function? So if we look at what's happening here with our x-intercepts, think about what these points are, right? So the first intercept is at 0, 0. The second one is at 2, 0. And so the reason we call them the zeros is because the value of y at these points is always 0. So because the value of y is always 0. Okay, so that's why we have that name for them. All right, so, that's back to the first page. So let's go over some key ideas as we move forward here. A quadratic equation is a polynomial with a second degree equation. So basically we're looking at anything that has this form where you have some kind of a number value multiplied by x squared, and sometimes that number value is 1, so you might not actually see it written in the equation, but remember that if you have no number, if it's just x squared, the secret kind of invisible number there is 1. Plus bx, so b is a different number that's multiplied by x, and then plus c, and you can see there's no x there, so this is just going to be any number value. And altogether, those things should be set equal to 0. So you can solve a quadratic equation of that form by graphing it. And basically, once we start looking at graphing this, we start calling it a function rather than just an equation. So the equation is kind of like the number values with the variables that we can solve for algebraically, and then when we start looking at graphing it, we call it a function. It's still the exact same values and everything like that. It's just a little bit of a different name, and I'm not sure why they have to do that, but it's math, so I guess they want to make things tricky for you. So the solutions to a quadratic equation are called the roots of the equation. Okay, and this is going to be a word you're going to see a lot in this chapter, so make sure you're really comfortable with that word. So solutions basically mean what are the possible number values of x, okay, and we call those the roots. Now, again, with this being math, there's going to be more than one name for that. So you can find the roots, or we call them the zeros, like we mentioned on the previous page, of a quadratic equation by determining the x-intercepts. So both roots and zeros are referring to x-intercepts of a graph. Okay, just different names. And the reason why those different names are around is again related to whether we're looking at an equation or a function, like on a graph or just solving algebraically. Roots is used when you're talking about an equation. Zeros is used when you're talking about a function. I wouldn't really personally worry too much about memorizing that differentiation. I would just make sure you know roots and zeros, you're basically always solving for what are the values of x, whether you're doing that algebraically within an equation or a function graphically, same thing. You're just looking for the x-intercepts, okay? So actually there's kind of like 3 different names for this: roots, zeros, or x-intercepts. Quadratic equations can have no real roots, which means there's no x-intercept. They could have one real root, which means they basically just touch the x-axis at one point, or they could have 2 real roots, which means that they cross the x-intercept at 2 different points. Okay, and so when we're looking at 2 different roots, or sorry, yeah, let's go through the different like possibilities here. So let's start in order. So first we're looking at no real roots. What does that look like? No, I'm just going to write no roots because it's easier. So with no roots, that means we have no x-intercept. And because with a quadratic equation, we're always looking at a parabola shape, that basically means that the parabola either has to be kind of like this, and don't mind the fact that my parabolas are definitely not going to be symmetrical. Okay, so you could have one that opens downwards, but you can see that this graph is never going to get high enough to reach the x-intercept, or you can have one that opens upwards, like this. And again, we can see that it's never going to go down low enough to cross the x-axis. So both of these are types of graphs that have no roots. They basically don't come in contact with the x-axis. Now the other thing we could have is one real root, or one root. And that's where the graph basically just at the vertex touches the x-intercept, and then it arches away again. So basically, let's say we had one here with 4, and oh, I hate drawing parabolas. Okay, there we go. So basically, even though, my drawing is terrible, we're going to assume that this only just hits the graph at the point of +4 on the x-axis, and that's our only root. Okay, you could have it obviously pointing down as well. Okay, now the last option is to have 2 roots. And basically what's happening there is you have a graph that's going up and around, right? So now this is, again, not symmetrical, because otherwise it should have gone through +4. But basically we have it crossing the x-intercept at -4 and at +6, which is not a proper quadratic, but that's okay. So essentially the whole point of 2 roots is just that the graph comes across the x-axis at 2 different points. Okay? So those are our possibilities. So let's look at some examples of this. Determine the zeros of this graph. And so with the graph already drawn for you, it should be pretty straightforward. We have 0 is the dark line, and then we have a blank and then -2. So of course halfway between that would be -1. So we can say x is equal to -1. Or this one has 2 roots, right? Because we see it crossing again here. So x is going to be between 2 and 4, which would be 3. So we can say x is equal to 3. And again, look to the filled in notes for a proper filled in version of this if you want a little bit more detail there. Okay. Next one, determine the roots of the quadratic equation. So this time we're not looking at a function. We're looking at just the numerical equation. Okay. However, what we can do, because this whole section is all about solving just using graphs, we'll look at how we solve the equations a little bit later on algebraically. So basically what you want to do is use your calculator for this. So let's do some practice with that. So you want to go back into y equals, clear out whatever you had in there before. And then we want to start entering in our graph. So x squared minus 6x minus 6x and then plus 9. Okay, so go into your graph. Hopefully it kind of shows up within that window that you have. Also, if your windows are all off, I'm pretty sure I went over this in a previous lesson, but just to make sure, if your windows were off and you couldn't see it, you can go into zoom. So you don't have to hit second function, just zoom. And then if you go to Z standard, this is going to basically bring you to like the standard settings, which is -10, +10, +10, -10, right? So basically the same for the X and the Y. And as we move forward, we'll look at some different options that you have for window settings, but for now this should work. So we use our graphing calculator and we see this. We're looking for the roots. So basically we're just looking for the x-intercept. And again, I have all these instructions written out on the filled in notes, so you can check there if you need to. But we want to figure out basically where is it touching the x-intercept. So let's see. That means I want to solve for second function trace, 0, and then so left bound. I'm to the left of the vertex there, so I can hit enter. And then just make sure you're quite sure that you're on the right side of the vertex, which seems pretty obvious there. And then hit enter one more time for guess. And so it tells us our 0 is 2.999. So basically you could just round it to 3 when y is equal to 0. Okay, so we would say x is equal to 3. And then it also tells us to verify your answer. So when you're verifying your answer, basically what you want to see is if you plug this value that you got from your graph into the equation, does it work out to equal to 0? So if we put in x squared, where x is 3, it's going to be 3 squared minus 6 times by x, which was 3. So 6 times 3, and then plus 9. And that should give us 0. 3 squared is 9. 6 times 3 is 18, plus 9 equals 0. So 9 minus 18 gives us -9, plus 9 gives us 0. So we can see that that works. So our verification basically proves that x is equal to 3. Okay. All right, let's look at some more complex. So starting to look into word problems, which usually most students find a little more complex. So in this example, we have a manager at a store that has determined the function f of x is equal to 600 minus 6x squared, models the expected weekly revenue in dollars from sweatshirts as the price changes. X is the change in price in dollars, and so R is the revenue. What price increase or decrease will result in no revenue? So basically we're trying to figure out for no revenue, remember R is going to be oh, I probably should have written this in. I think that was my mistake. This should be Rx, not Fx. That makes way more sense. So revenue is going to be the Y value, essentially. And then X, of course, is our X value on the graph. So we want to figure out which one will result in no revenue. So think about what that means. If our revenue is on the y-axis and we have none, what does that mean? Well, it means that we're looking for points on the graph where y is equal to 0, right? And the only places where y is equal to 0 is at x-intercept. So basically that means we're looking for roots or x-intercepts. Okay, so we want to graph this to start out with. So let's go back to y equals, clear out what we had, and enter in our equation. So 600 minus 6x squared. 6x squared. And go to the graph. So right away you can see that this setup that we have here in terms of the window is not going to work because you can see like the beginning of the graph going up here and then coming back down there. So we're going to need quite a bit bigger of windows. Sometimes what you can do here is go into zoom, and you can go to 0, which is zoom fit, and this will kind of move your graph so that it mostly fits everything in there. I'm not sure exactly why, but sometimes it doesn't seem to quite get it all in there. So Zoom Fit can be a good place to start, but if you can't see the whole graph, sometimes it means that you might want to go into your window settings, and now you can see what it's chosen for your window settings to fit it. So Y max is 600, X minimum is -10 and 10. So if you felt like you needed a little more space around the graph to see exactly what was going on, once you see this, you can know, right? Like, so if you needed a little more space above the graph, then you could always change this like Y max to 650. And now if we go back, we can see how the top of the graph isn't like right at the very outer edge of our window. Sometimes that's kind of nicer to work with. And same thing with these intercepts, right? So you can see that they're basically right at the edge. And because when you're calculating them, you need like a left bound and a right bound. You might want to move those out a little bit as well. So we can go back to the window and say if X is -10, let's maybe change it to -15 and X maximum to 15. And then we go back to the graph, and now you can really clearly see all the points of the graph. Oh shoot, now I wasn't really thinking though, because we might also want a little bit below that, because if we're looking for our left bound and right bound, we always have to move below the axis. So let's do one more adjustment here. So Y minimum, let's make it maybe -5. Ooh, that's pretty small, but whatever, it should be good enough. Okay, so we want to determine the zeros, so remember that's always going to be second function calculate. We want to go to 0, and then for our left bound, we want to go, sure, and then right bound, oops, shoot, sorry guys, 0, left bound, right bound, and 0. Okay, so we can see that our first 0, so it asks us to graph, so we can do a quick little kind of sketch here. And we're going to go kind of like that. Another one of my great drawings. So our point here is -10 on the x-axis and 0 on the y. And then if we go to the other side, probably we can assume that it's going to be +10, but we should do it just to be sure. So go to your 0, choose your left bound. You can play around a little bit. I think it shouldn't really matter if you did your left bound way over where it started, but I just prefer to do it closer just to be more precise. And then hit enter one more time for guess. So yeah, we were right. This is going to be +10 and 0 for our other intercept. So our zeros are x equals -10 and +10. Those are our zeros. What do these values mean? So we need to think back to what they were telling us in the word equation. What was x representing? X is the change in price in dollars. Okay, so they are the change in price. And because we're trying to relate change in price to revenue with this, right, we have X is our change in price and it's affecting our revenue. They're the change in price that results in what kind of revenue? Results in, well, because the y-axis is 0 on both of these, it would be the change in revenue that, or the change in price that results in 0 revenue or no revenue. Okay. Next one, do both price changes make sense? So basically the price changes then would mean you're dropping your price by $10, right? Because -10, or you're increasing your price by $10. And both of those result in 0, let's see, in 0 revenue. Now, if we think about what's happening over here, because, I mean, technically you could do a drop in price of 10, if like depending on what the sweatshirt was, right? Like, so if the sweatshirt was like $50 to begin with, yes, you could drop the price by $10. But if you look at what's happening over here, since quite a bit earlier, since like a 0 drop in price, the revenue, oh, wait a minute. Sorry, I was thinking about negatives here. It's only negative in the drop in price. The revenue is still positive. So still you could have, I was thinking about the Y. So yeah, you could have a drop in price of $10 and you're still in the positives for revenue. It's just that it's dropping down to 0. Or you could have an increase of $10 and that is still in the positive revenues but dropping off down to 0. So I would say both price changes make sense. The only kind of like qualifier you might want to put in would be obviously that the original price had to be more than $10, because if you drop the price by $10 and they were originally $10, you'll have $0, right? So yes, as long as the original price was over $10. Original price was over $10. Okay. All right, next one here, solve 3x squared minus x minus equals -2 by graphing. Now, with this one, you have to be careful because when you go into your y equals, what they're always assuming here is that whatever equation you've entered here, they're assuming that it's equal to 0. And we can see that in this equation, we have a polynomial that is set as being equal to a number value. So before you can enter this into your graphing calculator, you have to move the number value over to the other side, leaving a 0 on that side. So of course, if we have 3x squared minus x is equal to -2, if we want to move that -2, it means we have to add 2 to both sides. -2 plus 2, right? So -2 plus 2 is going to give us 0. And now we have our function 3x squared minus x plus 2. We want to solve for this, so let's put it in 3x squared minus x plus 2. Go to your graph. Wow, look at that. Our settings from our last graph work for the window. Okay, so now we want to solve for, it looks like this is going to be a one solution or one root equation, but let's go in and just make sure. So if we go to second function trace, 0, left bound, right bound, and then guess. What's going on there? Let's see. Second function 0, left bound, right bound. No, calculations are not detecting a sign change. Okay, maybe I just need to go in and change my window really quickly. Maybe I'll do like a y minimum of -10, and I might change this to like 15 because we probably don't need it to be quite that big. Oh, there you go. So you can actually see here now when we zoom in a little bit more. So this is why it's a good idea to be comfortable with playing around with your windows. When it was that big, it looked like it was touching, but that's because the scale was different, right? So now when we look at this, we can see that it actually doesn't touch the x-intercept. So then we would say that the solution to this is no real roots. Okay, and so if you needed to graph it, you could just go which doesn't look quite like what we saw there, but it's at least it kind of demonstrates the general shape of the graph that it opens up. So even like on tests, unless it asks you to be really specific, you can just show the general shape of the graph without worrying too much about the artistic component, because I sympathize with not being able to show that. Okay, so one more word question. Suppose the cable of a suspension bridge is modeled by the function HD equals 0.0025 times by x minus 100 squared minus 12. What is the horizontal distance between the two towers? Okay, so essentially if we look here, we've got towers. Maybe I'll use my highlighter real quick. So we have this tower here, right? Sorry guys, my headphones cut out. So we have the tower, and then what else do we have? Well, you can see we're looking at talking about the cable of a suspension bridge. So this is our cable. And if you look at this shape, what does it look like? Well, hopefully you can see that it's supposed to look like a parabola, right? And so essentially, if we think about, oops, I'm losing my highlighters. Okay, so essentially what we would think of here is we have a place where we're starting from, right? And then there's this kind of baseline of the bridge, and we're looking at how these cables touch down, right? And we want to solve for the distance between these two towers, so the distance between here. So let's see. First of all, we want to solve by graphing. So let's go into our calculator and enter in our function. So we have, just make sure this is on the screen here, 0.0025 and then bracket x minus 100 bracket square it and then minus 12. Okay, so now if we go to our graph, it's probably not going to fit super well on there. No. So let's go to zoom and try doing the zoom fit and see if that helps us out at all. Yeah, see, so sometimes it'll fit for like basically probably about half of the parabola. So let's go into our window settings and look. So for our X maximum right now, it's set to 15. Let's maybe make that into, actually, let me have a look here. 15, okay, so I'm going to go really far out. I'm going to go like 60 and see what that looks like. I'm not sure where that's supposed to be coming up on the other side. Let's have a look here. X minimum minus 60. Let's do our Y minimum because it looks like it's dropping down a lot. Minus 60. Let's see how that looks. Still not great. Okay, Windows, let's go to X. We don't really need to have the X minimum. It looks like set that low, so let's go minus 10. And let's go 100, let's see. Ooh, okay. I'm just going to double check here. 0.0025, x minus 100 squared minus 12. Okay. Window. Let's make this like 500. See what that does. And then Y minimum. Let's make it like minus 10. Okay, there we go. So now I can play around. I'm going to make this a little bit smaller because I can see that that went pretty long, and I'm going to make my Y's a little bit bigger. So my Y minimum, I'm going to make it minus 20, and my X maximum, let's make it 300. See what that does. There we go. That's pretty nice. Okay, so now we have this, and we kind of want to see what our x-intercepts are, right? So if you think about this part here is representing the cables, like it said. The cables are represented by this function, and we want to solve for the distance between the cables. And so what you can see here is that, let's see, the cables are going to be, if you have the cables going down and then back up, so you would assume that these the x-intercept here is where these cables are being attached. So basically what you would be looking at is, I'm going to add that in. Now that we can see the graph, this part here would be the x-axis, right? X-axis. And then these 2 points are the x-intercepts. So those are x-intercepts. Okay. So now we just need to solve for the values. So you want to go into your trace function, solve for 0, and then you want to do, sure, we can start with this guy, left bound, and then right bound and guess. So we end up, for the one on the right here, we end up with x equals positive 169.28203. And for the other one, we end up with, so second function trace, 0. We want to go left of that other intercept. Hit enter. Right of the intercept, hit enter, guess, and we end up with x equals 30.717968. Now, this is the kind of question I was mentioning earlier where if you don't have an x-intercept that's starting at 0 and you're looking for the distance between the two, right, because it's asking you what is the distance between these two towers. So keep in mind you need to find the difference between these two then. So we're going to have 169.28 minus 30.717 is going to give us, 169.28203 minus 30.717968 gives us 138.56. 138.56, and they wanted it to the nearest tenth, so we'll round that to 6, 138.6, and the units are meters. Okay, so of course for a written question I would expect you to write the towers are 138.6 meters apart from each other. Okay, so that's an introduction to how to solve quadratic functions graphically. And next time we're going to start looking at factoring, so solving quadratic equations rather than functions. So remember, equations is talking about the non-graphing component when we're looking at solving them algebraically. So we'll start out in our next lesson with a little bit of review from factoring that you would have done in Math 10C. So I'll see you in that lesson.